Hello, my name is Mike Loboyle. I am a graduate student at the University of Illinois at Urbana-Champaign. I would like to talk about a discontinuous collocation method I have been involved in developing and its application to the gravitational self-force problem. The lead of this project is Charalampos Markakis at Queen Mary University of London and Cambridge. Also working on this project are Leor of Southampton, Pablo Brubeck at Oxford, and Lydia Gomez da Silva at Queen Mary. The problem we are considering is the TEUKOLSKY or REGGE-WHEELER equation. This is a strongly hyperbolic partial differential equation for a scalar function that describes linear perturbations to the Kerr and Schwarzschild spacetimes. Many authors have shown that if a point particle is included in this equation with an appropriate choice of source term, the solution can be used to calculate the gravitational self-force on that particle in an appropriate gauge. So to solve this problem, a common approach is to transform it to the frequency domain. In this case, it separates into angular harmonics, and the radial part of the solution can be solved as an ordinary differential equation. This approach works best for circular or nearly circular orbits, where only a few frequencies are needed. However, if one wishes to consider highly eccentric or unbound orbits, then one finds that hundreds to thousands of frequencies are needed, greatly increasing the computational cost and also introducing subtle numerical difficulties into the problem. So to handle these problems, it would be best to directly solve this equation in the time domain. And so this problem has received a great deal of attention in recent years. To solve a hyperbolic partial differential equation in time, one typically uses the method of lines. First, one performs a reduction of order, taking the original second order in time partial differential equation and representing it as two partial differential equations that are first order in time for the field and for its time derivative. So with these two first order equations, one can then discretize the problem. That is, represent the field quantities U on a discrete grid and represent the derivative operators L as spatial differentiation matrices. So the most common discretization methods and the differentiation operators that result assume that the function in question is smooth. However, if a point particle is added to the TEUKOLSKY equation, it requires one to include a delta function or a distribution. This can be shown to cause the function C to be discontinuous and for all of its derivatives to be discontinuous. So now the problem is how to represent these delta functions on a finite grid. One approach that was explored is to approximate the delta functions as narrow Gaussian pulses, and then using continuous discretization methods. However, this approach was shown to lead to large errors in the solution. Others have found a finite difference representation of these delta functions. However, this representation is specific to a second order in space discretization, and it is unclear how this generalizes to higher orders or how it would be implemented in a pseudospectral method. The most successful method to date has been domain decomposition, where one chooses coordinates where the particle is stationary, and then uses two separate grids on either side of the particle. So we essentially have a Lagrangian picture where the particle is stationary and the coordinates and grid is time dependent. And one can then impose jump conditions at the location of the particle. Although this has been shown to be a very accurate method, it is very complicated and very difficult to implement computationally. As an alternative, Markakis and Barak have had the idea of introducing an Eulerian picture as opposed to the Lagrangian picture. That is, introducing a method where the coordinates in grid are held fixed and the particle is allowed to move freely in the domain. And then the field is represented by a single domain-wide discontinuous interpolation function. So to represent this discontinuous function, we can do it by taking advantage of the fact that the jumps can be computed in advance directly from the field equation. And so we can construct an interpolation function that satisfies the usual collocation conditions and also represents these jumps computed in advance known from the location of the particle. The method that is used is similar to one of Lagrange interpolation, so we review it here. In Lagrange interpolation, one wishes to find a polynomial of degree 1 less than the number of grid points that approximates the function over an entire domain. So it can be represented as a polynomial of the appropriate order with a set of undetermined coefficients, Cj here. To proceed, one can impose collocation, that is, require that the polynomial take the value of the original function at each of the grid points. This yields a set of algebraic constraints that can be solved to obtain the usual Lagrange interpolation formula. To handle the discontinuous problem, we take this idea, but instead of a single polynomial, we use a piecewise polynomial. That is, a polynomial whose coefficients change depending on which side of the particle we are on. So to proceed, one uses the usual collocation conditions, but now since we have more coefficients than we have collocation conditions, we need additional constraints. These are obtained from the jump conditions that are known in advance from the equation, from the original field equation. And so, with an appropriate number of algebraic constraints, it is possible to solve it and obtain a single piecewise polynomial that interpolates across the entire domain. The form of it is the usual Lagrange interpolation formula, but also a correction function that accounts for the jumps, represented by delta here. With this piecewise discontinuous interpolation function, we can use it to determine how to represent derivatives on our discrete grid. On taking derivatives of the interpolation function, we find that we get the usual pseudospectral derivative operator acting on the function values, as is common, but we see that the correction function adds an offset to the result one would usually obtain with just a pseudospectral derivative matrix. And so, since the form of the correction function is known, this enables us to simply modify an existing implementation of a finite difference or pseudospectral method that includes the discontinuities by just adding this offset. And of course, in principle, one can use this to approximate integrals to the function. To give a concrete example of these methods, we represent the fields one would need to solve for the scalar cell force on a static particle in the Schwarzschild spacetime, for which an analytic representation is available. We see that with a Lagrange interpolation polynomial, the standard one, it struggles to converge near the cusp of the function. However, when the discontinuous interpolation formula is used, we see that it captures the behavior at the cusp quite well. In this case, we used equidistant nodes, and so there's a Runge phenomenon near the boundaries of the function. If instead one uses the Chebyshev-Gauss-Lobato nodes, we see smooth convergence to the cusp and everywhere across the domain of the function. So we can study the convergence of this discontinuous interpolation function. We see that when considering the maximum or L infinity error as a function of the number of grid points used, the Lagrange interpolation does not converge as more grid points are added, represented here by m equals -1. However, when jumps are included, we see that as more grid points are added, the discontinuous interpolation converges to the function in question. But something interesting happens. One would expect that as one includes more jumps in the interpolation formula, the accuracy of the function would improve. However, we find that beyond a certain point, as more jumps are added, the accuracy decreases again. So we find that there's a rule of thumb that the optimal number of jumps to include are half the number of grid points. So if one was using a 64-point grid, it will be best to use around 30 or 32 jumps. This has all discussed how these discontinuous functions are handled in space. If we want to use this method to evolve a partial differential equation, then it is also necessary to consider how these discontinuous functions are handled in time. So to handle the time integration, it is most common to use an explicit method such as classical Runge-Kutta, because they are very straightforward to implement. However, they suffer from a number of drawbacks, such as not respecting the features of the original equation of motion in terms of the physics. So they are generally not time-symmetric, and they generally do not conserve energy in conservative systems. And in addition, they are conditionally stable. That is, the time step that one can use suffers a CFL limit. So to handle the time integration, we chose to consider a set of implicit time-symmetric methods, such as the trapezium rule, its higher order generalizations, and composition methods like Suzuki-Yoshida. These methods have the advantage of numerically conserving energy, and they are also unconditionally stable. That is, they do not suffer from a CFL limit. So usually implicit methods are avoided because they are more computationally expensive than explicit methods in general. However, for linear PDEs, and if one is using a pseudospectral spatial discretization, it is possible to construct implicit schemes that yield explicit recursion formulae by taking advantage of the fact that linear systems allow one to perform matrix inversions. And so there is no extra computational cost when compared to an explicit method. So for this reason, we have chosen to pursue these implicit methods to perform the time integration. But because the function is discontinuous, we need to consider the fact that the time integration must handle the discontinuity in the function as well, and that standard integration schemes assume the function is smooth. We showed that it's possible to correct the class of integration schemes derived before by using a method similar to how we obtained the discontinuous formula in space. For example, if we include jumps in the time direction, then we were able to derive this generalization to the trapezium rule that includes both the jumps in the function and its first time derivative. And so we use these schemes to construct a method of lines discretization. The problem we considered is one proposed by Field and coworkers, where one in the REGGE-WHEELER equation sets the potential to 0, and so obtains effectively a scalar wave equation in flat spacetime. The advantage of this problem is that it has an exact solution, and so we are able to give the problem exact initial data. Here we demonstrate that using the discontinuous interpolation method in space with Chebyshev-Gauss-Lobato points and evolving it in time with a discontinuous trapezium rule, we can capture the behavior of the particle and the radiation it produces in the field. So the grid is stationary, but the particle is moving, and the jumps in the derivatives of the function are accurately captured. In performing a convergence analysis, since the trapezium rule is known to be second order in time, we expected our discontinuous generalization to also be second order. And indeed, we see that it displays second order convergence in time. So to summarize, we have developed a high accuracy discontinuous interpolation method that allows one to use pseudospectral nodes that is in an Eulerian picture. It's not necessary to perform domain decomposition. The grid is fixed and stored. The particle can move freely inside the domain. And this gives one the freedom to choose their own coordinate system as opposed to being fixed to particle history coordinates. For example, instead of adding hyperboloidal layers to the boundary, one can use hyperboloidal slicing over the entire domain. In this case, the method is efficient and it's easy to implement. However, some things to keep in mind are that to obtain the high accuracy, it's necessary to compute a large number of jumps in advance, half the number of grid points one is using. And then that it's also necessary to update the correction function as the particle moves through the domain. So since Barak and Guidis have shown that one can use a scalar Hertz potential to directly construct the gravitational self-force, we believe that this proves to be a very promising route to self-consistent evolution under the influence of GSF. Thank you very much.